Hello, I'm glad to share our work, APQ, Joint Search for Network Architecture, Pruning, and Quantization Policy. As we all know, there's an emergent need of specialized networks for efficient deployment. For many years, researchers have been seeking ways to do this design. One typical example is by a pipeline as above: model architecture design followed by model compression, which concerns pruning and quantization. Admittedly, such a sequential pipeline can significantly reduce the cost of existing models. However, careful hyperparameter tuning is required to obtain optimal performance. The number of hyperparameters grows exponentially when we consider the three stages in the pipeline together, which will soon exceed acceptable human labor bandwidth. To tackle the problem of hyperparameter tuning, there comes a trend of automatic design for compact models. A typical pipeline is shown as above. For example, proxyless NAS/AMC/HAQ can be performed in 3 stages. For sure, this automatic design saves human labor, but what about other aspects? First, this is a multi-stage optimization problem, which can lead the solution to be suboptimal. Second, a considerable search time and energy consumption will be taken. For example, simply pipelining proxyless NAS/AMC/HAQ together will take 300 GPU hours. For a new deployment scenario, we should search again, so this kind of method can still take a large amount of time. We begin by revisiting the sequential design for compact models. As one can see, the design method sequentially does auto model specialization, auto channel pruning, and auto mixed precision quantization. The intermediate targets are assigned by a human, which turns out to be suboptimal. To this end, we combine these 3 separate stages together and propose a predictor-based method called APQ to jointly search the optimal model. There is no intermediate target involved in the APQ framework. Here's the APQ framework for joint optimization. For architecture search, we first train a highly flexible once-for-all network that supports not only the operator change, but also fine-grained channel change so that we can perform joint search over architecture and channel number. For the mixed precision search, due to the orthogonality for architecture versus quantization, and the time-consuming fine-tuning which is required for quantized accuracy evaluation, we instead apply a quantization-aware accuracy predictor to predict the accuracy after quantization. To do that, we start by building large-scale full-precision datasets. Each pair is denoted as architecture accuracy. We use the once-for-all network and directly evaluate a sampled architecture to collect data. After getting the data, we use it to train a full-precision model accuracy predictor. Meanwhile, we build a small-scale dataset with each data point denoting quantization policy, architecture, accuracy. We extract the architecture from the once-for-all network, do fine-tuning after setting the quantization policy, and then do evaluation to get the accuracy after quantization. After getting the full-precision model accuracy predictor and quantized model dataset, we use the predictor transfer technique to get the quantization-aware accuracy predictor. To get hardware feedback, we measure the cost of each operation and build a lookup table. Then, for an architecture with quantization policy, we can query the table and add up all the cost up to get the predicted cost. Finally, we use evolutionary search with predicted accuracy and hardware feedback to jointly optimize architecture, pruning, and quantization policy. This slide shows the details of the predictor transfer technique. We first pre-trained a full-precision accuracy predictor that predicts accuracy via architecture embedding. The architecture embedding encodes the information of the architecture like kernel size, channel number, etc. Then, we add another head representing quantization and use the pre-trained weights of the full-precision accuracy predictor to further fine-tune the whole model to get the quantization-aware accuracy predictor. We compare our method with 3 separate optimizations, which are proxyless NAS for auto model specialization, AMC for auto channel pruning, and HAQ for mixed precision quantization. While our method can directly do all the optimizations and overall achieve a more optimal result. Also, our method cuts down on the marginal search time by 4 orders of magnitude compared with MNAS-Net. We also compare with mixed precision models searched by HAQ under the latency/energy constraints. When the constraints are strict, our model can outperform the fixed precision model by more than 10% accuracy and 5% compared with HAQ. Such performance boost may benefit from the dynamic architecture search space, rather than a fixed one such as MobileNet v2. That's all for APQ, and thanks for listening.